NASA now acknowledges this. Its Mars orbiter captured unprecedented images of Interstellar Visitor 3 Censored Atlas. Meanwhile, China has already pushed a 302-frame sequence to the public, yet the high-resolution HiRISE shots remain locked in place, caught in bureaucratic limbo, while planetary defense rumors swirl and researchers raise alarms. Why is the year's most anticipated space dataset still hidden? Inside the pressure, the silence, and the stakes for science, the truth behind this standoff is stranger than it looks. Confirmation arrived quickly. NASA officials stated that the Mars Reconnaissance Orbiter's HiRISE camera did image interstellar object 3.1 Atlas during its close pass by Mars on October 3, 2025. The images are real, not speculative, and their existence is now on the record. For the first time, a spacecraft orbiting another world aimed its most powerful imager at an object from beyond our solar system. That alone is historic. Yet while China's Tianwen-1 released a full 302-frame run of the encounter, NASA's images are still unavailable to the public and the global science community. Questions multiplied as word of the freeze spread. NASA's explanation is procedural. The U.S. government shutdown that began October 1st halted most non-essential work, including scientific data processing and release. By law, only tasks tied to spacecraft health and safety could continue. HiRISE data, though safely stored, couldn't move through calibration, validation, and public posting. For weeks, the world waited while the files sat in NASA's pipeline. Transparency became the focal point as others filled the vacuum. China's space agency published its Mars orbiter imagery of 3.1 Atlas, a bright, compact coma, a white point with a faint halo, shot from roughly the same standoff range NASA planned. Lower resolution than HiRISE, yes, but the speed and openness highlighted the contrast. Online, planetary defense alert rumors took off. NASA has issued no warning, no upgraded alert for 3.1 Atlas. Public statements say the object poses no threat to Earth. The focus remains scientific. The supposed maximum alert looks unsubstantiated, more speculation than action by the Planetary Defense Coordination Office. Pressure is mounting from several directions. U.S. Representative Anna Paulina Luna has said NASA will release the HiRISE images once the government reopens and internal reviews are done. Harvard astrophysicist Avi Loeb has posted open letters arguing that timely data access is essential, especially when anomalies could challenge existing theory. For now, the images stay under lock and key, seen only by a small mission team. The world waits as scientific, political, and public stakes continue to rise. The pipeline itself runs on precision, routine, and compliance. When the shutdown hit at midnight October 1st, nearly all non-essential NASA operations stopped. This wasn't preference, it was federal law. Only work, protecting life, property, or national security could continue. For HiRISE, that meant the spacecraft stayed monitored and safe. But the science flow halted. After the scheduled imaging on October 2nd to 3, raw data stored on board were downlinked during deep space network passes. Normally, those files would go to the HiRISE Ops Center at the University of Arizona for conversion, calibration, and quality checks. Then the science team reviews, validates, and preps public release, steps governed by strict protocols requiring staff who during a shutdown are legally off-duty unless exempted. No link in that chain, from ingest to calibration, validation, and posting, was deemed essential. Waivers are rare and typically reserved for national security or immediate risk issues, not routine science. Only spacecraft safety personnel remained active. Data analysis and public affairs did not. FOIA requests also slowed. No new internal communications about the HiRISE 3 Atlas set appeared during the freeze, and response times stretched. None of this is unique to 2025. Shutdowns in 2013 and 2019 showed the same pattern: emergency releases only for legal safety reasons, not general science interest. Without a presidential or congressional override, the rules are absolute. Result: HiRISE images, fully acquired and safe, stayed locked until the government reopened and the full team returned. Public pressure grew as days passed without a single HiRISE frame. In Washington, Reppers Luna said plainly, NASA is expected to release the 3 Atlas images once reopened, and reviews are complete. Her statement echoed through science media and social channels, turning delay into a trust issue. She framed it as transparency. Discoveries of this magnitude belong to everyone, not just the few who control the pipeline. Avi Loeb pressed from the outside. He argued that science advances by chasing anomalies and gathering new evidence. 3 Atlas, he said, is a gift, an opportunity for researchers, the public, and students to ask bigger questions. Loeb drew a line between the humility to learn and the arrogance of expertise. Openness isn't a courtesy, it's core to science. His message resonated with journalists, educators, and citizen scientists who see 3 Atlas as a test of big science openness. Transparency campaigns multiplied. Advocates and science communicators circulated petitions urging NASA to publish ASAP. Many pointed to China's rapid Tianwen-1 release as a contrast, arguing U.S. leadership depends as much on openness as on engineering. Others warned that prolonged delays feed conspiracy theories and erode trust in the stewards of humanity's space enterprise. The images became a symbol of transparency, international competition, and the public's right to witness only the 3rd interstellar visitor ever recorded. October 3, 2025 offered a rare window. As 3 Atlas swept past Mars at minus 29 million kilometers, geometry put it within reach of our best off-Earth. Cameras. For HiRISE, the high-resolution imaging science experiment on MRO, this was a test of timing and engineering. HiRISE pairs a 0.5 mm aperture with a 12 mm focal length, built to resolve sub-meter features on Mars. At tens of millions of kilometers, physics sets hard limits, but the science value stayed high. 3 Atlas is only the 3rd confirmed interstellar object. Unlike its predecessors, it passed close enough to a major planet for direct imaging from orbit. With HiRISE, the aim was to capture coma structure, measure the brightness profile, and refine the trajectory with unmatched precision. Each frame could test comet activity models, hunt for jets or outbursts, and probe subtle structure Earth-bound telescopes can't resolve. At Mars distance, HiRISE could theoretically deliver more 1830 moisture pixel on a target like 3 Atlas, at least twice as sharp as Tianwen-1's 38.7 cm camera, and far beyond Hubble's 1,000 km pixel from Earth orbit. Practically, the nucleus would still be unresolved, a bright point in a compact, diffuse coma. But HiRISE could give the cleanest look at the inner envelope and near-nucleus environment. Months of planning aligned the schedule with closest approach. Exposure times had to be short, often 1s, to avoid motion blur. Tracking was pushed to the limit. No instrument around Mars or Earth could resolve the nucleus surface at this distance, but HiRISE could still measure brightness gradients and catch asymmetries or fragmentation. The urgency was simple. Opportunities to image an interstellar object from another planet's orbit are vanishingly rare. Even modest gains in resolution can change models and set benchmarks for future campaigns. As Tianwen-1 moved quickly to publish, all eyes turned to NASA's higher res set, knowing it could unlock new insight into 3 Atlas's nature and origin. The window closed in hours. The questions it raised will shape planetary science for years. Tianwen-1's release landed fast. A complete 302 frame sequence from 29 million kilometers, a time-lapse of a bright point-like core inside a faint symmetric halo. No jets or fine structure at that range. The nucleus unresolved. Still, the sequence let researchers measure coma brightness profiles and estimate overall extent. Early analyses by Chinese and international teams agreed. Point-like core, broad symmetric envelope, no obvious fragmentation during the window. Just as important was timing and openness. By publishing the full set within days, Tianwen-1 enabled global scrutiny, rapid orbit refinements, and broad public engagement. Students and citizen scientists stacked frames, built animations, and posted results, often their first experience with raw spacecraft data. In the absence of NASA's sharper HiRISE frames, Tianwen-1 became the primary record of 3 Atlas during the Mars encounter. It didn't resolve the nucleus or reveal fine details, but it offered a consistent, empirical snapshot from a unique vantage point. The rapid release underscored a growing expectation. Rare, high-profile targets merit open, immediate data to accelerate collaboration across borders. 9 distinct anomalies continue to circle 3 Atlas, many still unconfirmed. Preliminary spectra hint at elevated nickel relative to iron, but calibration issues and low SNR could mimic that signal. The trajectory is hyperbolic, consistent with interstellar origin. Small, non-gravitational terms remain within known comet behavior. No published orbit solution shows truly anomalous motion. Coma and tail structure drew attention. Briefings cite a compact, bright coma with little filamentary detail. NASA statements echoed Avi Loeb's early note of an unusual tail, but specifics, dust, ice mix, or odd brightness profile, remain unquantified. No current images, including Tianwen-1's, resolve the nucleus. Even HiRISE at 29 million kilometers won't do that. What it can do is constrain coma size, profile, and subtle asymmetries. Other claims, odd rotation, early activity onset, unexpected reflectivity, rest on limited or preliminary datasets. Most professionals urge caution. So far, nothing clearly outside comet norms. Validation, calibration, peer review, and cross-agency checks take time, especially for rare, distant targets. Looking ahead, discovery velocity is about to jump. The Vera Rubin Observatory's LSST will scan the southern sky to unprecedented depth every few nights. Upgrades to the Atlas network expand coverage and sensitivity. Together, they may boost interstellar detections from once in years to 1 or 2 per year. More visitors means more mysteries, and more need for open data and global teamwork. Right now, the sharpest images of an interstellar visitor sit out of public reach, not for lack of capability, but for lack of transparency. As LSST and next-gen surveys widen the net, open access becomes the real frontier. In a universe that grows a little less mysterious every day, withholding data keeps us in the dark. In Cosmos, we trust.